Have you ever really stopped to think about what happens when you write a piece of code and hit run? I mean, how does a machine, a hunk of metal and electricity, actually understand what you're trying to tell it? Well, today, we're going to pull back that curtain and get right into the magic of how your code is brought to life.
Okay, look at this. We've all typed this exact line, right? It's pretty much the first step for any programmer. It seems so simple. You type it, and boom, hello world pops up on your screen. But what's happening under the hood? What's the secret translation that happens between your keyboard and that final output? That is the big mystery we are solving today.
So, here's our game plan. We're going to start with the computer's native tongue, its secret language. Then, we'll talk about the bridge we build from our world to the machines. After that, we dive into the main event, the two big translation methods. We'll even look at a cool modern hybrid. And finally, see how it all comes together in the real world.
All right, let's kick it off. Section 1, a computer's secret language. This is all about the fundamental problem we're trying to solve. Take a look at this. On the left, you've got a simple human idea. Add 5 plus 3. We get it instantly. But on the right, that's what the computer actually sees. At its very core, a computer only speaks in zeros and ones, binary. That crazy-looking string of digits is how a machine might process our simple math problem. Now, can you imagine trying to write a whole application in that language? No way, it'd be a nightmare. This is the gap we need to cross.
So, how do we cross that gap? Well, that's where programming languages come in. They're the bridge. And as we're about to see, they exist on a whole spectrum, from languages that feel almost like English, all the way down to ones that are much, much closer to the machine.
So, on one end of that spectrum, you have what we call low-level languages. You can think of these as basically whispering directly into the computer's ear. They give you an incredible amount of control, letting you manage the processor and memory directly, but man, it is a very difficult dialect to learn and speak.
And here are the trade-offs, plain and simple. Because you're so close to the metal, your code runs incredibly fast. But it's super hard to write, and it's not portable. Code written for one type of CPU won't work on another. This is why you only really see it in places like operating systems or specialized drivers, where every single nanosecond of performance is critical.
Now, on the other, far more popular end of the spectrum, you've got high-level languages. These are the ones designed for us, for people. They use words and logic that feel natural, just like that hello world example we started with.
The advantages here are massive. The code is way easier to read and write, which means it's also easier to fix when things go wrong. And this is huge. It's portable. You can write your code once and run it on a Mac, a Windows PC, you name it. The only catch? All that convenience means there's a big translation step involved, which can make things a little bit slower.
This chart really lays it all out. High-level wins on readability and portability, no contest. But low-level, it absolutely dominates when it comes to raw speed. So it always comes back to this one fundamental question. Are you optimizing for the programmer's time or for the machine's performance? And that brings us to the main event, Section 3, the Great Translation. We've got our human-friendly code, and we know the machine needs binary. So how do we get from one to the other? Well, there are two classic solutions, compilers and interpreters. Let's start with the compiler. Think of a compiler like a super thorough translator. You hand them an entire book written in French, they go away, and they come back with a perfectly translated English version. The whole job is done up front, before a single reader opens the cover. That finished English book is a separate thing, ready to go. And it's a pretty intense process. The compiler scans everything, checks the grammar, makes sure it all makes logical sense, and even tries to optimize your code to make it run faster. Only then does it generate that final machine code file, your program. And remember, all of this happens before you run anything. Now, the payoff for all that upfront work is huge. The final program is lightning fast because all the translation is already done. Plus, it catches a ton of errors for you ahead of time. The downside? Every time you make a tiny change, you have to wait for the whole thing to recompile, which can kind of slow down your workflow. You'll find compiled languages behind the scenes of the most demanding software out there. We're talking about high-octane video game engines, the core of your operating system, basically anything where speed is the absolute top priority.
Okay, so what's the other way? The interpreter. Now, if a compiler is a book translator, an interpreter is more like a live translator at the UN. They listen to one sentence, immediately translate it, and say it out loud, then they wait for the next sentence. It's all happening in real time, one piece at a time.
Yeah, the process is a lot more direct. The interpreter reads a line of your code, translates it, executes it, and then just moves on to the next line. It's this simple, continuous loop that happens while the program is actually running. The beauty of this approach is how fast it makes development. You can change one line and see the result instantly. It's also often easier to debug, because if there's an error, the program just stops right on the problem line. The trade-off, as you can probably guess, is speed. That constant, on-the-fly translation adds overhead, making the program slower overall.
Interpreted languages are absolutely everywhere, especially when you want to build and test ideas quickly. Think about data scientists using Python to experiment with models, or pretty much the entire interactive web, which is powered by JavaScript. It's all about that rapid feedback loop.
But hold on. What if you didn't have to choose between the speed of a compiler and the flexibility of an interpreter? What if you could have the best of both worlds? Well, that's exactly where modern programming has taken us. Welcome to our fourth section, the incredibly clever hybrid called JIT compilation.
Just-in-time, or JIT, compilation is a total game changer. It starts off acting like an interpreter, so your program boots up quickly. But here's the clever part. It watches your code as it runs. It identifies the parts that are being used over and over again, the hotspots, and it compiles just those sections into super fast machine code right there on the fly. So the more you use the program, the faster it gets. This is the magic that makes things like Java and modern JavaScript so fast and responsive.
Okay, so let's land the plane. For our final section, Code in the Wild, let's connect all these ideas to the actual software you and I use every single day.
This table just nails it. Your computer's operating system or a graphics-heavy game engine, they need every drop of performance, so they're compiled. A dynamic, interactive website, it needs to be flexible but also feel snappy, which makes JIT compilation perfect for its JavaScript. And what about a data scientist exploring a dataset with Python? Fast experimentation is way more important than raw speed, so an interpreter is the right tool for the job. You see, the method always fits the mission.
So from a humble hello world all the way to a blockbuster video game, you now know that every single piece of software goes on one of these incredible translation journeys. So the next time you launch an app or open a website, just take a second and think about it. Was this code compiled for raw power, interpreted for flexibility, or did it get the best of both worlds? Pretty cool to think about, right? Thanks for tuning in.